Chapter 1. Introduction to Statistics. Statistics is the science of collecting, organizing, analyzing, and interpreting data. In everyday life, people constantly encounter data in the form of numbers, percentages, graphs, and claims. Statistics provides tools to make sense of this information and to draw meaningful conclusions while recognizing uncertainty. At its core, statistics is about decision-making. Individuals, businesses, researchers, and governments use data to answer questions, test ideas, and predict future outcomes. Because data are often incomplete or variable, statistical reasoning helps separate reliable information from misleading impressions. A key distinction in statistics is between descriptive statistics and inferential statistics. Descriptive statistics focus on organizing and summarizing data. This includes creating tables, graphs, and numerical measures that describe what the data show. Inferential statistics go a step further by using sample data to make conclusions or predictions about a larger group, known as a population. A population includes all individuals or objects of interest in a study. A sample is a subset of the population that is actually observed. Because studying an entire population is often impractical or impossible, statisticians rely on samples to gain insight. The challenge is ensuring that samples accurately represent the population. Data can take different forms depending on what is being measured. Qualitative data consist of categories or labels, such as colors, genders, or types of products. Quantitative data consist of numerical values, such as heights, weights, or test scores. Quantitative data can be further classified as discrete or continuous, depending on whether values are counted or measured. Another important concept is the level of measurement. Data may be classified as nominal, ordinal, interval, or ratio. These levels describe how much information the data provide and determine which statistical methods are appropriate. Understanding these distinctions helps prevent incorrect analysis and interpretation. Statistics is widely used across many fields, including medicine, psychology, economics, engineering, education, and social sciences. In each case, statistics helps researchers draw conclusions while accounting for variability and chance. However, statistical results must be interpreted carefully, as poor data collection or biased analysis can lead to incorrect conclusions. Technology plays a major role in modern statistics. Calculators, spreadsheets, and statistical software make complex computations faster and more accurate. While technology reduces the burden of calculation, understanding statistical concepts remains essential for interpreting results correctly. Ethics is also central to statistical practice. Misleading graphs, selective reporting, biased sampling, and improper analysis can distort findings. Responsible use of statistics requires honesty, transparency, and respect for the limitations of data. Statistics does not provide absolute certainty. Instead, it offers tools for making informed decisions in the presence of uncertainty. By understanding basic statistical concepts, individuals can better evaluate claims, interpret data, and apply reasoning skills in both academic and real-world settings. This chapter lays the foundation for all topics that follow. As the course progresses, statistical tools will become more precise and powerful, but they all build on these basic ideas about data, samples, populations, and careful interpretation. Study questions. What is the difference between descriptive and inferential statistics? Descriptive statistics summarize data, while inferential statistics use sample data to draw conclusions about a population. Why are samples used instead of entire populations? Because studying entire populations is often impractical, and samples provide manageable ways to gain insight when properly selected. Why is ethical use of statistics important? Because misleading data collection or analysis can lead to incorrect conclusions and poor decisions. Chapter 2. Exploring data with tables and graphs. Once data have been collected, the next step in statistics is to organize and display them in ways that reveal patterns and relationships. Tables and graphs make large amounts of data easier to understand by summarizing key features visually and numerically. This chapter focuses on common methods for organizing data and the principles behind effective data displays. One of the simplest ways to organize data is with a frequency distribution. A frequency distribution lists the values of a variable along with how often each value occurs. When data sets are large, values are often grouped into classes to make patterns more visible. These groupings help identify where data tend to cluster and how they are spread out. Relative frequency distributions express frequencies as proportions or percentages rather than counts. This makes it easier to compare data sets of different sizes. Cumulative frequency distributions show how frequencies accumulate across values or classes, helping to identify medians, percentiles, and overall trends. Graphs provide visual representations that can reveal features not easily seen in tables. Bar graphs are commonly used for qualitative data, where categories are compared using bars of equal width. The height of each bar represents the frequency or relative frequency of the category. Pie charts also display qualitative data by dividing a circle into slices that represent proportions of the whole. While pie charts can be visually appealing, they are often less precise than bar graphs and should be used carefully to avoid misinterpretation. Histograms are used to display quantitative data. A histogram consists of adjacent bars representing class intervals, with bar heights indicating frequencies. The shape of a histogram can reveal important characteristics of the data, such as symmetry, skewness, or the presence of gaps. Frequency polygons are another way to display quantitative data. They connect points representing class midpoints and frequencies, creating a line graph that emphasizes the overall shape of the distribution. Frequency polygons are useful for comparing multiple data sets on the same graph. Time series graphs display data collected over time. These graphs are particularly useful for identifying trends, cycles, and changes over long periods. Time series graphs are commonly used in economics, finance, science, and social research. When creating graphs, it is important to avoid misleading displays. Improper scaling, distorted axes, or omitted context can exaggerate or hide important features. Honest and accurate graphing requires clear labels, appropriate scales, and proportional representations. Effective tables and graphs simplify complex data without sacrificing accuracy. The goal is to communicate information clearly and truthfully so that viewers can interpret results correctly. Poorly designed displays can confuse or mislead, even when the underlying data are valid. By learning how to construct and interpret tables and graphs, students develop essential skills for exploring data. These tools provide the foundation for more advanced statistical analysis and help build intuition about how data behave. Study questions. What is the purpose of a frequency distribution? To organize data by showing how often each value or class occurs. When should histograms be used instead of bar graphs? Histograms are used for quantitative data, while bar graphs are used for qualitative data. Why is it important to avoid misleading graphs? Because distorted displays can lead to incorrect interpretations of the data. Chapter 3. Describing, exploring, and comparing data. Once data have been collected and organized, statisticians use numerical measures to describe key features of the data. These measures help summarize large data sets and make meaningful comparisons. This chapter focuses on describing data using measures of center, measures of variation, and tools for identifying unusual values. A measure of center identifies a value that represents the middle or typical value of a data set. The most common measures of center are the mean, median, and mode. Each provides a different perspective on what is considered typical, and the choice of measure depends on the nature of the data. The mean is the arithmetic average of a data set. It is found by adding all values and dividing by the number of observations. The mean uses every value in the data set, but it is sensitive to extreme values, known as outliers. A single unusually large or small value can significantly affect the mean. The median is the middle value when data are arranged in order. If there is an even number of observations, the median is the average of the two middle values. The median is resistant to extreme values, making it a better measure of center when data are skewed or contain outliers. The mode is the value that occurs most frequently. A data set may have one mode, more than one mode, or no mode at all. The mode is particularly useful for qualitative data, where numerical averages may not be meaningful. Measures of variation describe how spread out the data are. Two data sets can have the same center, but very different levels of variability. Understanding variation helps interpret how consistent or diverse the data values are. The range is the simplest measure of variation. It is calculated by subtracting the smallest value from the largest value. While easy to compute, the range depends only on extreme values and does not reflect how data are distributed between them. The variance and standard deviation provide more detailed measures of spread. Variance measures the average squared distance of each value from the mean. The standard deviation is the square root of the variance and is expressed in the same units as the original data. These measures describe how far values typically deviate from the mean. When working with samples rather than entire populations, formulas for variance and standard deviation include adjustments to account for sampling variability. This distinction ensures more accurate estimates of population characteristics. Another important concept is the distribution of data. Data may be symmetric, skewed to the right or skewed to the left. In symmetric distributions, the mean and median are close together. In skewed distributions, the mean is pulled toward the tail. Percentiles divide data into 100 equal parts and indicate the relative position of a value within a data set. Quartiles divide data into 4 equal parts. The first quartile marks the 25th percentile, the second quartile is the median, and the third quartile marks the 75th percentile. The interquartile range measures the spread of the middle 50% of data values. It is found by subtracting the first quartile from the third quartile. This measure is resistant to extreme values and is useful for identifying outliers. Box plots provide visual summaries of data using quartiles, medians, and potential outliers. They allow for easy comparison between multiple data sets and highlight differences in center, spread, and symmetry. Outliers are values that differ substantially from most of the data. They may result from measurement error, data entry mistakes, or genuine variability. Identifying outliers is important because they can strongly influence statistical measures and conclusions. By using measures of center, variation, and distribution together, statisticians gain a more complete understanding of data. No single measure tells the whole story. Effective data analysis requires selecting appropriate tools and interpreting them carefully. This chapter builds essential skills for summarizing and comparing data. These tools form the foundation for probability, inference, and statistical decision-making in later chapters. Study questions. Why might the median be preferred over the mean in some data sets? Because the median is resistant to extreme values and better represents skewed data. What does the standard deviation measure? It measures how far data values typically deviate from the mean. Why are measures of variation important in data analysis? Because they describe how spread out the data are and help compare consistency across data sets. Chapter 4. Probability. Probability provides a way to measure uncertainty and to quantify how likely events are to occur. In statistics, probability forms the foundation for understanding randomness, making predictions, and drawing conclusions from data. This chapter introduces the basic rules of probability and the concepts needed for later statistical inference. A probability describes the likelihood that a particular event will occur. Probabilities are expressed as numbers between 0 and 1, inclusive. A probability of 0 means an event cannot occur, while a probability of 1 means an event is certain. Values between 0 and 1 indicate varying degrees of likelihood. An experiment is a process that produces outcomes. The collection of all possible outcomes of an experiment is called the sample space. An event is any subset of the sample space, which may consist of one outcome or many outcomes. Defining the sample space clearly is a critical first step in probability analysis. One common approach to probability is classical probability, which applies when all outcomes are equally likely. In this case, the probability of an event is found by dividing the number of favorable outcomes by the total number of possible outcomes. This method is often used for games of chance such as dice, cards, or coins. Another approach is empirical probability, which is based on observed data rather than theoretical assumptions. Empirical probability is found by dividing the number of times an event occurs by the total number of trials. As the number of trials increases, empirical probability tends to stabilize, reflecting the long-run behavior of the event. The law of large numbers explains this stabilization. It states that as the number of repetitions of an experiment increases, the relative frequency of an event tends to approach its true probability. This principle helps explain why probability models become more accurate with larger samples. Basic probability rules help simplify calculations. The probability of an event occurring is equal to 1 minus the probability that it does not occur. For mutually exclusive events, which cannot occur at the same time, the probability that one or the other occurs is the sum of their individual probabilities. Some events are not mutually exclusive and can occur together. In these cases, simply adding probabilities would double count the overlap. To correct for this, the probability of both events occurring is subtracted once to avoid overestimation. Conditional probability measures the likelihood that one event occurs given that another event has already occurred. Conditional probability reflects how new information changes the probability of an outcome. It is calculated by dividing the probability of both events occurring by the probability of the given event. Two events are independent if the occurrence of one does not affect the probability of the other. For independent events, the probability that both occur is found by multiplying their individual probabilities. Recognizing whether events are independent is essential for correct probability calculations. Tree diagrams and tables are useful tools for visualizing sequences of events and conditional relationships. These tools help organize complex probability problems and reduce errors in reasoning. Probability rules are widely applied in real-world situations, including risk assessment, quality control, medicine, finance, and decision-making. Understanding probability helps individuals interpret data, evaluate claims, and make informed choices under uncertainty. This chapter establishes the groundwork for probability distributions and statistical inference. Mastery of these concepts is essential for understanding how statistics models random behavior and supports conclusions drawn from data. Study questions. What is the difference between a sample space and an event? A sample space includes all possible outcomes, while an event is any subset of those outcomes. What does the law of large numbers describe? It explains how observed relative frequencies approach true probabilities as the number of trials increases. When are two events considered independent? When the occurrence of one event does not affect the probability of the other. Chapter 5. Probability distributions. Probability distributions describe how probabilities are assigned to the values of a random variable. Instead of focusing on individual events, probability distributions provide a structured way to understand the likelihood of different outcomes across an entire range of values. This chapter introduces random variables and the most common types of probability distributions. A random variable is a numerical description of the outcome of a random process. Random variables can be discrete or continuous. A discrete random variable takes on specific countable values, such as the number of defective items in a batch. A continuous random variable can take on any value within a given interval, such as heights, weights, or time. A probability distribution lists the possible values of a random variable along with the probability associated with each value. For discrete random variables, the distribution is often presented in a table. Each probability must be between 0 and 1, and the sum of all probabilities must equal 1. One important measure associated with a probability distribution is its mean. The mean of a probability distribution represents the long-run average value of the random variable over many repetitions of the experiment. It is found by multiplying each possible value by its probability and adding the results. Another important measure is the standard deviation of a probability distribution. The standard deviation measures how much the values of the random variable typically deviate from the mean. Distributions with larger standard deviations show greater variability, while smaller standard deviations indicate values clustered closer to the mean. The binomial probability distribution is a widely used discrete distribution. It applies to experiments that have a fixed number of trials, only 2 possible outcomes per trial, independent trials, and a constant probability of success. These conditions are often summarized as a checklist to determine whether the binomial model is appropriate. In a binomial experiment, the random variable counts the number of successes in a fixed number of trials. The binomial probability formula calculates the probability of obtaining a specific number of successes. While the formula can be complex, technology is commonly used to compute binomial probabilities efficiently. Binomial distributions are useful in many real-world situations, such as quality control, surveys, and reliability testing. They help quantify uncertainty when outcomes are classified into 2 categories, such as success or failure. Another discrete distribution is the Poisson distribution, which models the number of times an event occurs within a fixed interval of time or space. The Poisson distribution is useful when events occur independently and at a constant average rate. It is often applied to rare events, such as accidents, arrivals, or system failures. Continuous probability distributions differ from discrete ones, in that probabilities are associated with intervals rather than exact values. For continuous random variables, the probability of any single exact value is 0. Instead, probabilities are found by calculating areas under a curve. Understanding probability distributions allows statisticians to model random behavior and predict outcomes. These models form the basis for many statistical methods used later in hypothesis testing and estimation. This chapter provides the tools needed to describe randomness mathematically. By learning how probability distributions work, students gain a deeper understanding of variability and uncertainty in real-world data. Study questions. What is the difference between a discrete and a continuous random variable? A discrete random variable has countable values, while a continuous random variable can take on any value within an interval. What conditions must be met for a binomial distribution to apply? There must be a fixed number of trials, 2 outcomes per trial, independent trials, and a constant probability of success. Why is the standard deviation important in a probability distribution? It describes how much the values of the random variable typically vary from the mean. Chapter 6. The normal distribution. Many real-world datasets follow a predictable pattern known as the normal distribution. This distribution plays a central role in statistics because it describes how many natural and social phenomena behave. This chapter explains the characteristics of the normal distribution and how it is used to analyze data. The normal distribution is a continuous probability distribution with a distinctive bell-shaped curve. It is symmetric about its center, meaning the left and right sides mirror each other. The highest point of the curve represents the mean, which is also equal to the median and the mode in a normal distribution. One defining feature of the normal distribution is that its shape is determined entirely by 2 parameters, the mean and the standard deviation. The mean locates the center of the distribution, while the standard deviation controls the spread. Larger standard deviations produce wider curves, while smaller standard deviations produce narrower curves. Although normal distributions share a common shape, they can differ in scale and location. Changing the mean shifts the curve left or right. Changing the standard deviation stretches or compresses the curve without altering its symmetry. An important guideline for interpreting normal distributions is the empirical rule. This rule states that approximately 68% of data values lie within one standard deviation of the mean. About 95% lie within 2 standard deviations, and nearly all values lie within 3 standard deviations. This pattern provides a quick way to estimate probabilities and assess how unusual a value is. To compare values from different normal distributions, statisticians use standardized scores, often called z-scores. A z-score represents the number of standard deviations a value lies above or below the mean. Positive z-scores indicate values above the mean, while negative z-scores indicate values below the mean. Standardizing values allows comparisons across different datasets with different means and standard deviations. For example, test scores from different exams can be compared by converting them to z-scores, even if the exams use different scoring scales. The standard normal distribution is a special normal distribution with a mean of 0 and a standard deviation of 1. Tables and technology are used to find probabilities associated with z-scores in the standard normal distribution. These probabilities represent areas under the curve. Normal distributions are widely used to model measurement error, biological traits, test scores, and many other variables. However, not all data follow a normal distribution. Applying normal models to data that are heavily skewed or contain strong outliers can lead to incorrect conclusions. Statisticians often check whether data appear approximately normal using graphs such as histograms or normal probability plots. These tools help determine whether normal-based methods are appropriate. The normal distribution is essential for statistical inference. Many confidence intervals and hypothesis tests rely on normality assumptions or approximate normal behavior, especially with large samples. By understanding the normal distribution, students gain insight into how variability behaves in many situations. This chapter provides a foundation for inference techniques that rely on normal models to make predictions and decisions under uncertainty. Study questions. What are the key characteristics of a normal distribution? It is bell-shaped, symmetric, and determined by its mean and standard deviation. What does a z-score represent? It shows how many standard deviations a value lies above or below the mean. Why is the empirical rule useful? It provides quick estimates of how data are distributed around the mean. Chapter 7. Estimates and sample sizes. Statistical inference often involves estimating unknown population characteristics using sample data. Because samples vary from one to another, estimates are subject to uncertainty. This chapter explains how statisticians construct estimates, measure their reliability, and determine appropriate sample sizes. A point estimate is a single value used to estimate a population parameter. For example, a sample mean may be used to estimate a population mean, and a sample proportion may be used to estimate a population proportion. While point estimates are simple and easy to compute, they do not convey information about how accurate the estimate might be. To address this limitation, statisticians use confidence intervals. A confidence interval is a range of values that is likely to contain the true population parameter. Instead of giving a single estimate, confidence intervals provide a measure of uncertainty associated with the estimate. The level of confidence represents the long-run success rate of the method used to construct the interval. Common confidence levels include 90%, 95%, and 99%. A higher confidence level produces a wider interval, reflecting greater certainty at the cost of precision. Confidence intervals are constructed using a point estimate plus or minus a margin of error. The margin of error depends on several factors, including the confidence level, the variability in the data, and the sample size. Larger samples generally produce smaller margins of error. Interpreting confidence intervals correctly is essential. A confidence interval does not mean that the population parameter changes from sample to sample. Instead, it means that the method used to construct the interval captures the true parameter a certain percentage of the time when repeated over many samples. Sample size plays a crucial role in estimation. Small samples tend to produce less precise estimates with wider confidence intervals. Larger samples reduce uncertainty and improve reliability, but they also require more resources. Statisticians use formulas to determine the minimum sample size needed to achieve a desired margin of error at a given confidence level. These calculations help ensure that studies are neither too small to be useful nor unnecessarily large. The variability of the population also affects required sample size. Greater variability requires larger samples to achieve the same level of precision. When variability is unknown, preliminary studies or conservative assumptions are often used. Bias in sampling can undermine the accuracy of estimates, regardless of sample size. Even very large samples can produce misleading results if they are not representative of the population. Careful sampling methods are essential for valid inference. Estimation methods are widely used in polling, quality control, medical research, and social science. Understanding how estimates are constructed and interpreted allows consumers of statistics to evaluate claims more critically. This chapter highlights the balance between precision, confidence, and practicality. Effective statistical estimation requires thoughtful choices about methods, sample sizes, and interpretation. Study questions. What is the difference between a point estimate and a confidence interval? A point estimate is a single value, while a confidence interval provides a range of plausible values for a population parameter. How does increasing sample size affect a confidence interval? It reduces the margin of error, making the interval narrower and more precise. Why is representative sampling important for estimation? Because biased samples can lead to inaccurate estimates regardless of size. Chapter 8. Hypothesis testing. In many situations, the goal of statistics is not just to estimate a population value, but to evaluate a claim or make a decision based on data. Hypothesis testing provides a structured process for determining whether sample evidence supports or contradicts a specific claim about a population. A hypothesis is a statement about a population parameter. In hypothesis testing, two competing hypotheses are formulated. The null hypothesis represents a claim of no effect, no difference, or status quo. It is the assumption that any observed differences are due to random variation. The alternative hypothesis represents the claim being tested and reflects a meaningful effect or difference. The testing process begins by assuming the null hypothesis is true. Sample data are then used to assess how compatible the observed results are with this assumption. If the data are very unlikely under the null hypothesis, the null hypothesis is rejected in favor of the alternative. A key concept in hypothesis testing is the test statistic. The test statistic measures how far the sample result deviates from what is expected under the null hypothesis. The form of the test statistic depends on the type of data and the parameter being tested. Probability plays a central role in evaluating test results. The p-value represents the probability of obtaining a test statistic as extreme as, or more extreme than, the one observed, assuming the null hypothesis is true. Small p-values indicate that the observed result is unlikely under the null hypothesis. A significance level, often denoted by alpha, is chosen before conducting the test. Common significance levels include 0.05 and 0.01. The significance level represents the maximum probability of rejecting a true null hypothesis. If the p-value is less than or equal to the significance level, the null hypothesis is rejected. Hypothesis tests can be one-tailed or two-tailed. A one-tailed test considers departures in only one direction, while a two-tailed test considers departures in both directions. The choice depends on the wording of the alternative hypothesis and must be made before analyzing the data. Errors are possible in hypothesis testing. A type 1 error occurs when a true null hypothesis is incorrectly rejected. A type 2 error occurs when a false null hypothesis is not rejected. These errors reflect the uncertainty inherent in working with samples rather than entire populations. Statistical significance does not necessarily imply practical importance. A result may be statistically significant but have little real-world impact. Interpreting results requires consideration of context, effect size, and consequences. Hypothesis testing is widely used in science, medicine, business, and policy making. When applied correctly, it provides a systematic method for evaluating evidence and making informed decisions under uncertainty. This chapter builds the foundation for many specific hypothesis tests introduced later. Understanding the logic behind hypothesis testing is essential for correctly applying and interpreting statistical procedures. Study questions. What is the role of the null hypothesis in hypothesis testing? It represents the default assumption that any observed effect is due to random variation. What does a p-value measure? It measures how likely the observed result is if the null hypothesis is true. What is the difference between a type 1 and a type 2 error? A type 1 error rejects a true null hypothesis, while a type 2 error fails to reject a false null hypothesis. Chapter 9. Inferences from two samples. Many statistical questions involve comparing two groups rather than analyzing a single population. Researchers may want to know whether two treatments differ, whether two populations have different means, or whether two proportions are the same. This chapter introduces methods for making statistical inferences based on two samples. When comparing two samples, the goal is often to determine whether an observed difference reflects a real population difference or is simply the result of random sampling variation. Statistical inference provides tools to make this determination while accounting for uncertainty. One common comparison involves two population means. Depending on how data are collected, samples may be independent or dependent. Independent samples come from separate, unrelated groups. Dependent samples, also called paired samples, involve matched observations, such as measurements taken before and after a treatment on the same individuals. For independent samples, inference focuses on the difference between the two sample means. Confidence intervals can be constructed to estimate the difference between population means, and hypothesis tests can be used to evaluate claims about that difference. Variability within each sample affects the reliability of the comparison. For dependent samples, differences are calculated for each pair of observations. Statistical analysis is then performed on these differences rather than on the original data values. This approach reduces variability caused by individual differences and often increases the sensitivity of the analysis. Another common comparison involves two population proportions. For example, researchers may compare the proportion of successes in two different groups. Confidence intervals for the difference between proportions help estimate how much the populations differ, while hypothesis tests assess whether the difference is statistically significant. Assumptions play an important role in two-sample inference. These include randomness, independence, and appropriate sample sizes. Violating assumptions can lead to unreliable conclusions. Statisticians often check conditions using graphs, summaries, and context before performing calculations. Technology is widely used to perform two-sample inference. Calculators and statistical software compute test statistics, p-values, and confidence intervals efficiently. Even so, understanding the logic behind the methods remains essential for proper interpretation. Interpreting results requires attention to both statistical and practical significance. A statistically significant difference may not be meaningful in real-world terms, while a practically important difference may fail to reach statistical significance in small samples. Two-sample inference is used in a wide range of applications, including medical studies, product testing, education research, and social sciences. These methods allow researchers to evaluate differences and make informed comparisons based on data. This chapter extends the ideas of estimation and hypothesis testing to more complex situations involving multiple groups. Mastery of two-sample inference prepares students for advanced statistical analysis and real-world data evaluation. Study questions. What is the difference between independent and dependent samples? Independent samples come from unrelated groups, while dependent samples involve paired or matched observations. Why are paired samples often analyzed using differences? Because analyzing differences reduces variability caused by individual characteristics. Why must assumptions be checked before performing two-sample inference? Because violating assumptions can lead to misleading or invalid conclusions. Chapter 10. Correlation and Regression. In many studies, the goal is to understand the relationship between two quantitative variables. Rather than comparing groups, researchers may want to know whether variables move together and whether one variable can be used to predict another. This chapter introduces correlation and regression as tools for analyzing relationships between variables. A scatter plot is the primary graphical tool used to explore relationships between two quantitative variables. Each point on a scatter plot represents an observation, with one variable plotted on the horizontal axis and the other on the vertical axis. Scatter plots help reveal patterns such as direction, form, and strength. Direction describes whether the relationship is positive or negative. A positive association means that as one variable increases, the other tends to increase. A negative association means that as one variable increases, the other tends to decrease. If no clear pattern exists, the variables may have little or no association. Form refers to the overall shape of the relationship. Many relationships are approximately linear, meaning they follow a straight line pattern. Other relationships may be curved or irregular. Identifying the form is important because correlation and linear regression are appropriate only for linear relationships. Strength describes how closely the data points follow the pattern. Strong relationships show points tightly clustered around a line or curve, while weak relationships show more scatter. Outliers can greatly affect both the appearance of a scatter plot and numerical measures of association. Correlation is a numerical measure that describes the strength and direction of a linear relationship between two variables. The correlation coefficient, usually denoted by R, ranges from -1 to +1. Values near 0 indicate little or no linear association, while values near -1 or +1 indicate strong linear relationships. Correlation measures association, not causation. Even a strong correlation does not imply that changes in one variable cause changes in the other. The relationship may be influenced by a lurking variable or may be coincidental. Careful interpretation and study design are necessary to draw causal conclusions. Regression analysis builds on correlation by providing an equation that describes the relationship between variables. In simple linear regression, a straight line is used to model the relationship between an explanatory variable and a response variable. The regression line summarizes how the response variable changes as the explanatory variable changes. The equation of a regression line includes a slope and an intercept. The slope represents the expected change in the response variable for a 1-unit increase in the explanatory variable. The intercept represents the predicted value of the response variable when the explanatory variable equals 0, although it may not always have practical meaning. Regression can be used for prediction, but predictions are most reliable within the range of observed data. Extrapolating beyond this range can lead to inaccurate or misleading results. The strength of the relationship and the presence of outliers also affect predictive accuracy. Residuals measure the vertical distance between observed values and the regression line. Analyzing residuals helps assess whether a linear model is appropriate. Patterns in residuals may indicate nonlinearity, unequal variability, or other issues with the model. Correlation and regression are widely used in science, business, economics, and social research. These tools help summarize relationships, identify trends, and support data-driven decision-making. This chapter emphasizes both the power and the limitations of correlation and regression. When used correctly, they provide valuable insight into how variables are related, but careful interpretation is essential to avoid false conclusions. Study questions. What information does a scatterplot provide? It shows the direction, form, and strength of the relationship between two quantitative variables. Why does correlation not imply causation? Because an observed association may be influenced by other variables or coincidence rather than a direct cause and effect relationship. What does the slope of a regression line represent? It represents the expected change in the response variable for a 1-unit increase in the explanatory variable. Chapter 11. Goodness of fit and analysis of variance. Some statistical questions involve comparing observed data to expected outcomes or comparing more than two groups at once. This chapter introduces goodness of fit tests and analysis of variance, which extend hypothesis testing to more complex situations. A goodness of fit test evaluates whether observed data match a specific theoretical distribution. Instead of comparing means or proportions, this test examines how well a model fits the data. It is commonly used when data are classified into categories and expectations are defined in advance. The chi-square statistic is the key measure used in goodness of fit tests. It summarizes the overall difference between observed frequencies and expected frequencies across all categories. Larger values of the statistic indicate greater disagreement between the data and the model. To conduct a goodness of fit test, expected frequencies must be sufficiently large in each category. This requirement ensures that the chi-square approximation is valid. If expected frequencies are too small, the test results may be unreliable. The chi-square distribution is used to determine p-values for goodness of fit tests. The shape of this distribution depends on the degrees of freedom, which are determined by the number of categories and any constraints imposed by the model. Another application of the chi-square method is testing for independence in contingency tables. In this context, the goal is to determine whether two categorical variables are related. Expected frequencies are calculated assuming independence, and the chi-square statistic measures how much the observed data deviate from that assumption. While chi-square tests are useful for categorical data, analysis of variance, commonly known as ANOVA, is used to compare means across three or more groups. Rather than performing multiple pairwise tests, ANOVA provides a single test that evaluates whether at least one group mean differs from the others. ANOVA works by comparing two sources of variability. One source reflects differences between group means, and the other reflects variability within groups. If the variability between groups is large relative to variability within groups, there is evidence that not all group means are equal. The test statistic used in ANOVA is called the F statistic. It is calculated as a ratio of between-group variation to within-group variation. Larger F values provide stronger evidence against the null hypothesis of equal means. ANOVA relies on several assumptions, including independent samples, normally distributed populations, and equal variances across groups. While ANOVA is fairly robust to moderate violations, serious departures from these assumptions can affect results. A significant ANOVA result indicates that at least one group mean differs, but it does not identify which groups are different. Additional analysis is required to make specific comparisons. These follow-up methods must be used carefully to control error rates. Goodness of fit tests and ANOVA are widely used in research, quality control, marketing, and social sciences. They allow analysts to evaluate models and compare multiple groups efficiently and systematically. This chapter expands the scope of hypothesis testing beyond simple comparisons. By learning these methods, students gain tools for analyzing categorical data and complex experimental designs. Study questions. What is the purpose of a goodness of fit test? To determine whether observed data match a specified theoretical distribution. What does the chi-square statistic measure? It measures the overall difference between observed and expected frequencies. Why is ANOVA used instead of multiple pairwise tests? Because it controls error rates while comparing means across multiple groups at once. Chapter 12. Nonparametric tests. Many statistical methods rely on assumptions about population distributions, such as normality. When these assumptions are not met, or when data are measured on an ordinal scale rather than a numerical scale, nonparametric tests provide useful alternatives. This chapter introduces nonparametric methods and explains when and why they are used. Nonparametric tests do not require specific assumptions about the shape of population distributions. Instead of relying on parameters such as means and standard deviations, these methods often use ranks or signs. This makes nonparametric tests especially useful for small samples, skewed data, or data with outliers. One common nonparametric test is the sign test. The sign test is used with paired data to determine whether there is a difference in medians between two related samples. Rather than measuring the size of differences, the sign test considers only whether differences are positive or negative. Another widely used test is the Wilcoxon signed rank test. Like the sign test, it is applied to paired samples, but it also takes the magnitude of differences into account by ranking them. This test is more powerful than the sign test when its assumptions are met. For independent samples, the Mann-Whitney U test provides a non-parametric alternative to the two-sample t-test. It compares the distributions of two groups by ranking all observations together and analyzing how ranks are distributed between groups. When more than two groups are compared, the Kruskal-Wallis test can be used as a non-parametric alternative to one-way ANOVA. This test evaluates whether samples come from the same distribution by comparing rank sums across groups. Non-parametric methods are also used to measure association between variables. Spearman's rank correlation coefficient measures the strength and direction of a monotonic relationship between two variables. It is useful when relationships are not linear or when data are ordinal. While non-parametric tests are flexible, they have limitations. Because they use less information from the data, they may be less powerful than parametric tests when parametric assumptions are satisfied. Choosing between parametric and non-parametric methods involves balancing robustness and efficiency. Interpreting results from non-parametric tests follows the same logic as other hypothesis tests. P-values are used to assess evidence against the null hypothesis, and conclusions must consider both statistical and practical significance. Non-parametric tests are widely applied in psychology, medicine, education, and social sciences, where data often violate strict assumptions. They provide reliable tools for analysis when traditional methods are not appropriate. This chapter emphasizes the importance of selecting methods that fit the data. Understanding non-parametric tests allows statisticians to analyze a broader range of situations while maintaining valid conclusions. Study questions. When are non-parametric tests preferred over parametric tests? When data do not meet distributional assumptions or are measured on an ordinal scale. What advantage does the Wilcoxon signed rank test have over the sign test? It accounts for both the direction and magnitude of differences, making it more powerful. Why might non-parametric tests be less powerful than parametric tests? Because they use less detailed information from the data. Chapter 13. Index of Difficulty, Ethics, and Quality Control. Statistics is not used only to analyze data after it are collected. It is also used to design fair measurements, ensure ethical practices, and maintain consistent quality in processes and products. This chapter introduces applied statistical concepts related to testing, ethics, and quality control. One application of statistics in education and psychology is the measurement of test difficulty. The index of difficulty measures how challenging a test question is by examining the proportion of students who answer it correctly. Values near 0 indicate very difficult questions, while values near 1 indicate very easy questions. Ideally, test questions are designed to have moderate difficulty so they can effectively distinguish between levels of understanding. The index of difficulty is often used alongside other measures, such as discrimination indexes, to evaluate the quality of test questions. Together, these tools help educators create assessments that are fair, reliable, and meaningful. Poorly designed questions can misrepresent student ability and reduce the validity of test results. Ethics plays a critical role in statistical practice. Ethical issues arise in data collection, analysis, interpretation, and reporting. Researchers must ensure that data are collected honestly without coercion or deception, and that participants' rights and privacy are protected. Misuse of statistics can take many forms. Selective reporting, misleading graphs, inappropriate sampling, and biased analysis can all distort conclusions. Even unintentional errors can have serious consequences if they influence decisions in healthcare, public policy, or business. Transparency is a key ethical principle. Statisticians and researchers should clearly explain methods, assumptions, limitations, and potential sources of bias. Clear communication allows others to evaluate findings and reduces the risk of misinterpretation. Quality control is another important application of statistics. In manufacturing and service industries, statistical methods are used to monitor processes and detect problems before they lead to defective products. These methods help maintain consistency and improve efficiency. Control charts are commonly used in quality control. A control chart plots data over time and includes reference lines that indicate acceptable levels of variation. Points that fall outside these limits may signal that a process is no longer operating as expected. Statistical quality control distinguishes between common cause variation, which is inherent in a process, and special cause variation, which results from specific, identifiable factors. Identifying the source of variation helps organizations decide whether corrective action is needed. Ethical responsibility extends to quality control as well. Failing to address known defects or manipulating quality data can endanger consumers and damage trust. Responsible use of statistics supports safety, fairness, and accountability. This chapter highlights how statistics influences real-world systems beyond academic analysis. By understanding measurement, ethics, and quality control, students see how statistical reasoning supports informed decisions and responsible practices. Study questions. What does the index of difficulty measure? It measures the proportion of individuals who answer a test question correctly, indicating how difficult the question is. Why is transparency important in statistical analysis? Because it allows others to understand methods, evaluate results, and avoid misinterpretation. What is the purpose of control charts in quality control? To monitor processes over time and detect unusual variation that may indicate problems. Chapter 14. Statistical Process Control. Statistical process control focuses on using data to monitor and improve ongoing processes. Rather than reacting to problems after they occur, statistical process control helps identify potential issues early and maintain consistent performance. This chapter explains how statistical tools are used to evaluate process stability and quality over time. A process is considered stable when its variation remains within predictable limits. Even well-designed processes naturally exhibit some variability. Statistical process control distinguishes between normal variation that is expected and unusual variation that signals a potential problem. Control charts are the primary tool used in statistical process control. A control chart displays data collected over time along with a center line representing the process, average, and control limits that define acceptable variation. These limits are not arbitrary. They are calculated using statistical principles. When data points fall within the control limits and show no unusual patterns, the process is said to be in control. Points outside the control limits, or patterns such as trends or cycles, may indicate that the process is being influenced by special causes that require investigation. Different types of control charts are used depending on the type of data being monitored. Some charts track measurements such as weight or length, while others track counts or proportions, such as the number of defects. Selecting the appropriate chart is essential for accurate monitoring. Statistical process control helps organizations reduce waste, improve efficiency, and maintain consistent quality. By identifying problems early, corrective actions can be taken before defects become widespread. This proactive approach is more effective than relying solely on final inspections. Interpreting control charts requires careful judgment. Not every fluctuation indicates a problem, and overreacting to normal variation can disrupt a stable process. Understanding the difference between common cause variation and special cause variation helps guide appropriate responses. Statistical process control is widely used in manufacturing, healthcare, service industries, and education. For example, hospitals may monitor infection rates, while schools may track performance trends over time. In each case, data-driven monitoring supports continuous improvement. Technology plays an important role in modern process control. Software systems automate data collection, chart creation, and analysis, making it easier to monitor complex processes in real time. However, understanding the underlying concepts remains essential for meaningful interpretation. Ethics and responsibility are also important in process control. Ignoring warning signals or manipulating data undermines the purpose of monitoring systems and can lead to harm. Accurate reporting and timely action are critical components of responsible process management. This chapter emphasizes how statistics supports quality and reliability in real-world operations. Statistical process control provides a framework for maintaining standards, identifying improvement opportunities, and making informed decisions based on data. Study questions. What is the main goal of statistical process control? To monitor processes over time and identify unusual variation that may indicate problems. What do control limits represent on a control chart? They represent statistically determined boundaries for expected process variation. Why is it important to distinguish between common cause and special cause variation? Because common cause variation is expected, while special cause variation requires investigation and corrective action. Chapter 15. Ethics in Statistics. Ethics is a fundamental component of statistical practice. Because statistical results influence decisions in science, business, medicine, education, and public policy, ethical responsibility is essential at every stage of the statistical process. This chapter focuses on ethical principles that guide the proper use of statistics and protect the integrity of data-driven conclusions. Ethical issues can arise during data collection. Researchers must ensure that data are gathered honestly and fairly, without manipulation or coercion. Participants should be informed about how their data will be used, and privacy and confidentiality must be protected. Failure to follow ethical guidelines can harm individuals and undermine trust in research. Sampling methods are another area where ethical concerns may arise. Biased samples can produce misleading results, even when calculations are correct. Deliberately excluding certain groups or misrepresenting who was studied violates ethical standards and can lead to incorrect or unfair conclusions. Ethics also plays a role in data analysis. Choosing inappropriate statistical methods, ignoring assumptions, or selectively reporting favorable results can distort findings. Analysts must resist pressure to manipulate data to support predetermined conclusions. Graphical displays and summaries must be presented honestly. Misleading scales, omitted context, or exaggerated visuals can misrepresent the true meaning of the data. Ethical communication requires clarity, accuracy, and transparency so that audiences can interpret results correctly. Another ethical concern involves interpretation. Statistical significance does not guarantee practical importance, and correlation does not imply causation. Overstating results or making unsupported claims can mislead decision-makers and the public. Ethical interpretation involves acknowledging uncertainty, limitations, and alternative explanations. Technology has increased both the power and the ethical challenges of statistics. Large datasets and advanced software make it easier to analyze information quickly, but they also increase the risk of misuse. Ethical responsibility requires understanding both the tools and their limitations. Conflicts of interest must be disclosed. Financial, professional, or personal incentives can influence how data are collected, analyzed, or reported. Transparency about potential conflicts helps maintain credibility and trust. Education in ethics helps statisticians and data users recognize ethical dilemmas and respond appropriately. Ethical guidelines and professional standards provide frameworks for responsible conduct, but individuals must also exercise judgment and integrity. Ethical statistics supports informed decision-making and public trust. When data are collected, analyzed, and communicated responsibly, statistics becomes a powerful tool for understanding the world and improving outcomes. This final chapter reinforces the idea that statistical skill alone is not enough. Responsible practice requires ethical awareness, honesty, and respect for the impact that statistical conclusions can have on individuals and society. Study questions. Why is ethical data collection important in statistics? Because unethical collection practices can harm participants and lead to invalid or misleading conclusions. How can data presentation be unethical? By using misleading graphs, omitted context, or distorted scales that misrepresent results. Why is transparency important in statistical reporting? Because it allows others to evaluate methods, identify limitations, and trust the conclusions.